In Concept E, we're going to be focusing on principal energy level electron configurations. So by the end of this video, students should have a basic understanding of how to write principal energy level electron configurations. They should be able to determine the number of valence electrons in both atoms and ions, and also be able to draw Lewis dot electron diagrams to illustrate the valence electrons in atoms and ions. So these electron configurations, they tell us how the electrons are arranged around the nucleus by telling us the number of principal energy levels as well as the number of electrons in each level. Now these principal energy levels, we call the innermost energy level the first energy level, and then as we move further away from the nucleus, they increase in the amount. So first energy level, second, third, and so on. Now they can only have a maximum number of electrons for each principal energy level. So in the first one, which is the smallest and closest to the nucleus, we can only hold 2 electrons. However, the second principal energy level can hold 8, the third can hold 18, and the fourth can hold 32. Now all the electron configurations on the periodic table are neutral, and if you look at your periodic table and open it up, you'll see that each element has its own electron configuration. Now remember, it's neutral, so the protons are equal to the electrons, so we can be able to look at any atom's electron configuration. However, for ions, we know that there has been a loss or gain of electrons, so we're going to add or subtract electrons only from the last number in the electron configuration, so from the outermost shell. So we're going to try some of these out. So if you don't have it out already, take a look at your periodic table. Magnesium as an atom has the electron configuration of 282. And again, I'm just getting that off the periodic table. Now magnesium with a ion that has a +2 charge, that means it's lost 2 electrons. So the +2 charge means it's lost 2 electrons. So we take the 2 out of the outermost level so that we have the configuration 2,8. Bromine on the periodic table has the configuration 2,8,18,7. The -1 charge on its ion means that it's gained an electron, so it's going to gain it in the outermost energy level. So 2, 8, 18, and 8. Xenon is going to, if you look it up on the periodic table, and this is considered a noble gas in group 18, it has the configuration 2, 8, 18, 18, 8. Now, barium is fairly similar. It's just 2 atomic numbers higher, so you can see the addition of the 2 electrons in the outermost shell. Now, there is a shorthand, especially when we get to the larger elements. Having to write all this information every time is pretty time-consuming. So we can use what's called the noble gas configuration shortcut. So we find the noble gas that comes directly before that element. We compare the electron configurations. So this first 5 principal energy levels, we're going to represent with the noble gas in brackets, and then we add on any additional electrons that come after that. And we'll practice this more in class tomorrow, but it's just so you can start to get an idea of different ways that we can write these principal energy level configurations. Now, when we get later in the year to bonding and some other topics, we're going to be focusing on just what's called the valence electrons. These are the electrons in the outermost energy level, or outermost shell. So you can see with boron, which has a configuration of 2, 3, the 3 that are on the outside are called the valence electrons. The silicon has the 4, and antimony has 5. The valence electrons you're going to see are always going to be between 1 and 8. So going across the periodic table from lithium to neon, you can see that increasing number of valence electrons. Also, if an atom's valence level is full as an atom, then it's a noble gas, and it's found in the last column, number 18, on the periodic table. So these all have 8 valence electrons. Now this isn't in your notes, but just to point out some things, because this is going to come up again and again, noble gases are unreactive, or we say it's inert, because they have a full valence shell of 8 electrons as an atom. An element with a full valence shell is kind of like a happy element. It has everything it needs, so it doesn't have to gain or lose or share electrons in order to achieve that, perfect ideal number of 8 electrons. So elements with these full valence shells do not easily gain or lose electrons, so they won't participate in reactions or bonding. We just talked about the valence electrons, and very briefly, the kernel electrons are all the inner electrons, so all the non-valence electrons. So if we look at these 3 elements configurations, the valence electrons are just going to be the ones in the outermost shell. The kernel electrons are the sum of all the inner electrons. So for sulfur, you have 10 kernel electrons and 6 valence. For strontium, you have 36 kernel electrons and 2 valence. And then for gallium, you have 28 kernel electrons and 3 valence electrons. So it's just important, especially with the valence electrons, that you have an easy time picking out how many there are. Lewis dot diagrams we're going to be drawing this year to illustrate and represent various atoms and ions. The dots only illustrate the valence electron configuration, so the outermost shell. So we've already talked about the kernel and the valence electrons. Our Lewis dot diagrams are going to represent the kernel using the symbol of the element, and the valence electrons are going to be represented by dots or X's. So how we're going to go about doing this is you're going to look up or write down the element symbol. You're going to look up the electron configuration and only focus on the last number in that configuration, which is the number of valence electrons. You're then going to, now knowing that number, place a dot or an X to represent the electrons. And you want to put them on, kind of like you're looking at the face of a clock, at the noon, 3, 6, and 9 positions on the face of the clock. We always put the first two together, and then the remaining ones get spread out around those other 3 sides. So carbon, which has 4 valence electrons, we can represent either with dots or with X's. Now, if you're working with an ion, you have to adjust the valence electrons because, again, it's either gained or lost electrons. Now, I'm going to show you 2 examples of this. The big thing is that your final diagram has to include brackets around the symbol and potential dots, and also place a charge of the ion outside of the brackets. So for sulfur, we've added 2 electrons to the 6 electrons that normally sulfur has in its valence shell. So if you looked up sulfur as an atom, it has 6 valence electrons. The -2 means it's added in or gained 2 electrons. So you're going to see I represented the original 6 with dots and then the final 2 with X's. So it has a complete 8. I put this in brackets, and then I place the -2 charge on the outside of the brackets. You're going to see that negative ions always end up with 8 valence electrons showing. Now, a positive ion, this is when we have subtracted out 1 electron from the valence shell. Potassium only had 1 electron in its valence shell to start, so we end up with no dots around the K, the potassium. I place it in brackets, and then the +1 charge is placed on the outside of the brackets. You're going to see that positive ions always end up with 0 valence electrons showing. Now remember, technically it has an inner shell that's full, but based off of its original valence shell, we don't have any electrons there. All right, and that is it. So we're going to review again in class tomorrow the principal energy level configurations and spend time looking at the Lewis dot diagrams.